Part A is a really tough start to this question. You've got to remember that if you can't get it, you can still carry on with some of the other parts. That's one thing to note, because I think this is challenging. I'm just going to show you what I did when I did this question. It's actually not the best method, but it kind of gives some motivation. Sometimes when you don't know how to do something, I mean, of course, you might run out of time at this point, but if you do have time, sometimes you have to play around with things and see if you can get them to work. So I'm going to consider this triangle here in blue. And let OP just be, I'm just going to call it X for simplicity. That will necessarily be a right angle because the radius is meeting a tangent. And then this here is alpha. And we know in the answer we've got sine alpha, so I can write down that sine alpha is equal to, now this length is r because it's the radius of the first circle, so it's going to be r divided by x. And therefore r is equal to x sine alpha. And that's not great, but it's at least a starting point. If I now draw another circle, the next one along, the second circle essentially, then I can draw the center in, which will be R2. By the way, this length is also R. This length is R2. And I've got now, I'm not going to go over it, but I've got like a triangle here that I can see. And therefore sine alpha is equal to R2 over, and it's going to be that full amount, x, but then I'm minusing r, and I'm minusing r2 from it. And we can rearrange that, so it's going to be x, I can multiply through basically, so it's going to be x sine alpha minus r sine alpha minus r2 sine alpha will equal r2. Now we know that this thing here is equal to r because we just showed it. So I can actually write r and factorize that out, 1 minus sine alpha equals, and then I can add the r2 sine alpha over and factorize out the r2. It's going to be 1 plus sine alpha. So from that you can see if you do, well, the first term was r, the second term was r2, so you're going to have to do the second term divided by the first term. Then we're going to get r2 divided by r1 is 1 minus sine alpha over 1 plus sine alpha. So it's kind of seems to be working. The thing is, we've only shown that relationship is true for between the first circle and the second circle, and we need to show that it's always true. So you could do the second and the third and see if that works. But we want like a slightly, want a general way of showing it. And I'm going to show you now how to do that. But this is a good starting point at least, and it kind of gives you the idea of drawing some triangles. So the way to actually deal with it is not to have this big triangle here and sort of have this x that we need to eliminate, but just look at two circles together. And I've copied this across. Okay, and then I'm just enlarging it. Now this is the same picture as before, so we still have alpha here. It's just now I've got two circles with their different centers, and I'm going to draw a triangle that looks like this. Do you know what? I'm going to draw it accurately. So horizontal line and a vertical line. Now this is alpha, and therefore, because they're similar triangles, this is also alpha. And I will add the hypotenuse on as well. There we go. And I'm interested in sine alpha again. Now, here's the thing. To the point here, this distance, that's going to be Rn, the radius. Meanwhile, this distance is going to be Rn plus 1. And hence, this part of the triangle is going to be Rn. The opposite is going to be Rn minus Rn plus 1. And then we're divided by the hypotenuse. And this is good because I don't have to include some other length. I'm just going straight for it. And the hypotenuse is in fact simply going to be this distance, which is Rn, plus this distance here, which is Rn plus 1. And I'm not done, but I've at least now got a relationship between two different terms. Remember, we want to work out what Rn plus 1 over Rn is. That's the goal. So multiply through by the denominator. And then we want to basically get Rn plus 1 as the subject. So we can add Rn plus 1 onto the left-hand side and factorize out 1 plus sine alpha. And then subtract Rn sine alpha from both sides and factorize out the Rn, and we'll get 1 minus sine alpha. And actually we're nearly there. So this implies that this equals this. Whew, that is tough, I think. But what we have just shown is that the radii will form a geometric sequence with this common ratio. I'm not going to write all that out. I'm just going to say the result follows. Remember, this is the radii of the n plus 1th circle, and this is the radii of the nth circle. And so to get if you have Rn and then Rn plus 1, if you want to know what you're timesing by, then you just simply take that term and divide it by that term. So that's what we've shown. Okay, well done if you managed to figure that out especially in a short space of time, because I think it needs quite a lot of playing around with it. Looking at the next part, we're asked to find, in terms of R and alpha, the total area enclosed by all the circles, simplifying your answer. So this area plus this area and so on. And there's actually an infinite number of circles. So we've got this infinite geometric series to add, essentially. So the area is going to be pi r squared is my first one, plus pi r2 squared, that's my second circle, and so on. Now, we've just said that the relationship between each term is that we just times by this every time. Remember, that was the sequence for the radii, and now we've got the radii squared. So the next one is going to be, well, it's going to be r, but then we need to times that by 1 minus sine alpha over 1 plus sine alpha. But then we need to square the whole thing. And what that's going to mean is that we square the r and we square this factor. The next one in the sequence is that we then, well, whatever the radius was, it was r times this fraction. You would then times by the fraction again. And so if you're squaring that, you would, well, the radius would be r times this fraction squared. So when you square that radius, you're going to get r squared, and you're going to get 1 minus sine alpha over 1 plus sine alpha. Now, when you square the square of something, we're going to get to the power 4. And that is how it's going to continue. So be really careful. Even though it forms a series, I just want to write the series down. That would help. So the series was r, and then r times this, times this fraction. I'm just going to call it 1 minus s and 1 plus s. And the next one is going to be r 1 minus s over 1 plus s all squared. Now remember, we're not actually interested in that sequence, we're interested in the square of the sequence. So it's going to be this squared, and this squared. That's just another, I'm just trying to justify why it's to the power 4. And that'll be to the power 6, and so on. So factorize out the pi r squared in capitals, and then it's going to become I think it's fine to abbreviate. Okay, this bit here is a geometric series. A is equal to 1. R is then going to be 1 minus s over 1 plus s all squared. And the sum to infinity is a over 1 minus r. So the whole thing is going to be pi r squared 1 over 1 minus s over 1 plus s all squared. I can put this over a common denominator. Remember, I'm being asked to simplify it. So it's going to be, or maybe I times top and bottom by 1 plus s squared. Okay, I could have put it over a common denominator and flipped it around, but this will give the same answer. Now, technically, we have the difference of two squares. If you have x squared minus y squared, then that is equal to x plus y, x minus y. So I'm going to get 1 plus s plus 1 minus s multiplied by 1 plus s minus 1 plus s. I've done this minus this. I've just dealt with the negatives. Here, the s's cancel. Here, the 1's cancel. So my final answer is going to be pi r squared 1 plus sine alpha all squared all over 2. Oh wait, it's going to be 2 times 2 sine alpha, it's going to be 4. Sorry, my pen is, come on, 4 sine alpha. Okay, that is a powerful result. Remember, alpha could be any angle between 0 and pi over 2. Nice one. On to part C. We're told that the area inside the quadrilateral PAOB, so that's this kite essentially, not enclosed by parts of C1 or any other circle, is S. We're asked to show that S is this. Now this is starting to look like it's going to get quite brutal. I mean, we thought A and B were tough, right? We've now got cot and coset going on. But the principle doesn't seem too bad. So basically, we want to know it's this area, this area. We want to know all this purple stuff added together. And to do that, I think we're going to need to basically, first of all, find the area of the kite. So we've got the area of a triangle, and then we can just double it. It's going to be length PA times R, and then halving that, but then we're going to double it to get the area of the kite. So basically, kite area is going to be PA times R. Now the question remains, how do we get PA? Sorry, I'm moving about a little bit. There's no straight answer for that. However, we can get PO because PO is just well, it's not quite all of the circle radii added together. It's the first radius plus 2 lots of the second radius plus 2 lots of the third radius, and so on. So find PO. Sorry, back to the bottom. We can find PO, we can then use Pythagoras. I've already forgotten. I think P was here. Yeah, A was here. O was here. So we have that this is R. So PO is R plus 2 lots of R2 plus 2 lots of R3, and so on. And we can write that as 2 lots of R plus R2 plus R3, and then we can just minus R at the end. And remember, we have this relationship between the radii because they form a geometric series. So it's going to be R plus R1 minus sine alpha over 1 plus sine alpha. And then we just times by that again. Factorize out the R. Okay, we've got another infinite geometric series. A is 1, R this time is 1 minus S over 1 plus S. So that means the sum to infinity is 1 over 1 minus S over 1 plus S times through by 1 plus S. And I think we've got 1 plus sine alpha over 2 sine alpha. So the full area is going to be 2R plus sine alpha over 2. That's going to cancel with that. This will equal, okay, let's keep going. Surely it's got to simplify. So I can basically separate it into two different fractions. I'm going to get R times 1 over sine alpha, which will be cosec alpha, plus R times sine alpha over sine alpha, which is just R, and then I'm minusing R. So this is our answer. Now remember, that was our answer for PO. So if I want PA, it's going to be R squared cosec squared alpha minus R squared, because I'm finding the shorter side, square rooted now we just need to remember, like, is there an identity involving this? Well, we got sine squared plus cos squared is 1. If we divide through by sine, we get 1 plus cot squared is going to be cosec squared. And therefore cosec squared minus 1 is cot squared. And so this simplifies really nicely and amazingly to R cot alpha. That is our PA, and therefore the kite area is going to be R squared cot alpha. Now, there's still more to do. So we are interested in this purple area. We've worked out this kite area, and we also know the full area of the circles. So the shaded area is going to be the kite area minus the area of all the circles, but then we are going to have to work out this green area here and add that back on. So it might be worth trying to calculate that now, in fact. This is going to be 90 minus alpha, because the whole thing must add up to 180. That will also be 90 minus alpha. And so this angle here, I know the whole thing is 360, so it's got to be 180 plus 2 alpha. I just remembered, actually, we're working in terms of radians, so it's going to be pi. Let me change this to pi over 2, sorry. So this area of the sector, sorry, this angle for the sector is pi plus 2 alpha. Okay. I don't know what to call this. This is the area enclosed by PAOB, but not contained in the circles. It's going to equal my r squared cot alpha, that's my kite, minus, and then I'm going to need to minus that thing I found here. That was my area of all the circles. So I'm just trying to grab it so I don't have to write the whole thing out again. But remember, like I said, we also now need to add on the area of the sector. So it's going to be pi r squared is the area of that whole circle, but I'm going to times by the fraction. So it's going to be pi plus 2 alpha all over 2 pi. It's a fraction. So I'm trying to scroll down the page. It's not. There we go. Now we need to try and simplify this. So first thing I can do is factorize out r squared. And here I've taken out the r squared. I'm going to have pi over 4. And there's no hint of squaring anything in the answer, so I'm going to need to expand this out. And then here, well, this pi cancels with this pi. So I've got pi over 2 plus alpha. I can separate this, so it's going to be pi over 4 sine alpha when I just consider the first term and divide through by sine alpha, plus pi over 2, because when I do pi over 4 times 2 sine alpha over sine alpha, the sine answers cancel, so I'm just left with pi over 2. But actually, this should actually be a minus. And then I'm going to minus pi over 4 times 1 over sine alpha, which is cosec alpha, plus the pi over 2 and plus alpha. These cancel, and we are left with r squared. I'm going to write it like it says in the answer, alpha plus cot alpha minus pi over 4 cosec alpha minus pi over 4 sine alpha. One word to sum all of this up. Wowzers. We have 2 parts left to go. 5, 3, 5. Okay. Well, we've got what S is, and naturally, if you couldn't quite get there, you can still take the result and try and finish it off. So we're now essentially asked to differentiate with respect to alpha. As I'm scrolling down, it keeps jumping back to the top. We can just pass the r squared through as a constant, so I'm going to leave that outside the bracket. Differentiate alpha, that gives 1. Then we have to differentiate cot alpha. Got to try and remember this one. So I remember that tan goes to sec squared. Cot, does it go to plus or minus cosec squared? I think it's minus. So it's 1 minus cosec squared alpha. Then got pi over 4 going through. Differentiate cosec alpha. I remember that sec goes to sec x tan x, and cosec goes to, I think it goes to minus cosec cot. Of course, you can, if you've got the time, you can prove these. Prove these yourself. Let's just do it actually, just because I don't think I've convinced you that I know that. So let's let y equal 1 over sine x. This would be u, this would be v. dy by dx is, we use the quotient rule, so u dash v minus u v dash over v squared. So we get 0 minus 1 times cos. I haven't bothered to write down u, maybe I should. U dash is just going to be 0. V dash is cos x all over sine x, sine squared x rather. And that will be minus cos x over sine x, which is cot x, minus cot x. And then we got 1 over sine x in there as well. Okay, so you can't, it just takes a bit of time, doesn't it, when you're under time conditions. So finally, we just need to differentiate minus 1/4 sine alpha. Oh, sorry, that should have been, that becomes plus then, because cosec differentiates to minus, you get double negative. Okay, now doesn't quite look the same, does it? We're trying to factorize out a cot squared ultimately. We had that result from before for 1 minus cosec squared, and that was the same as cot squared, I remember. So we're going to get r squared cot squared alpha. Now we need to do something with this. We can see in the final answer, I've kind of dealt with this, with this part. I think I just made a mistake actually. Cosec squared minus 1. Where's it gone? Here we go. So cosec squared minus 1 is cot squared. So 1 minus cosec squared is minus cot squared. And that's what we have here. So this should be a minus, sorry. And that means I basically dealt with this part. Sometimes you just sort of spot these errors as you go along. I rushed that bit. You know, actually I don't have the whole page in front of me, so I can't just like quickly look back and see these identities. And then I've got a cos alpha, so I'm gonna factorize out pi over 4 cos alpha. I need more room than this. Okay, this is gonna go. Start that again. So we're going to get r squared. This bit here, like I was saying, is equal to minus cot squared alpha. And then I'm going to plus pi over 4, just because I see it in the answer, cos alpha. Need to do it on another line, I'm sorry. Now when I factorize, I will be dividing by, I need to take a bit more time, so I'm going to get cosec alpha cot alpha, but I need to divide by cos alpha. That's what I was trying to say. And then it's going to be minus 1. That's all multiplied by r squared. Now this thing here, remember, cosec, we're dividing by cos, so let's write this bit out in full. It's going to be 1 over sine alpha times cot, which is cos alpha divided by sine alpha, and then I'm dividing by cos alpha, so they are going to cancel. So this thing here is actually going to be, cosec squared alpha, and we just had that 1 minus cosec squared alpha was cot, so cosec squared alpha minus 1 is cot squared. So factorize that cot squared out. We're left with pi over 4 cos alpha minus 1. I'm sorry, that explanation was a little bit messy. I could have maybe done a bit better, but hey, look, I got there, all right? One final part, sheesh. Okay. Find in terms of R the least value of S for alphas between pi over 6 and pi over 4. Well, it's quite natural, I think, to look at the derivative first of all. And that's going to be when cot alpha is equal to 0, or cos alpha is equal to 4 over pi. And there's no solutions to this. In fact, cot alpha looks a little bit like this, and it only equals 0 at pi over 2. So there's no solutions on the interval. So we could substitute in pi over 6. I need to go onto another page, I'm sorry, because I've run out of space. We could substitute in pi over 6 and pi over 4 and see which is smaller. But we need to, how do we know? Well, we know there's no stationary point, don't we, actually? So it should be enough to substitute in pi over 6 and pi over 4 and see which is smaller. But we can do a little bit better than that. If you consider cot squared alpha, it's going to be greater than 0 on the interval, since cot alpha is. But it's decreasing. You can see that from the graph. So now we just need to look at pi over 4 cos alpha minus 1. Well, actually, this looks like this. It's also decreasing. Well, cos alpha is. So if we minus 1 from it, then in fact it's even going to be, it's going to look a bit like this. It's going to be less than 0 on the interval. And it's going to be decreasing too. The conclusion is that the least value will be when alpha is pi over 4. And we can now substitute in and find out what S is. We could substitute it into the derivative. We're not actually interested in that. We're interested in the least value of S. I've tried to make a comprehensive argument of why it's pi over 4. So now we're just left with putting pi over 4 into here. Tan of pi over 4 is 1, so cot of pi over 4 is also 1. Sine of pi over 4 is 1 over root 2, so cosec of pi over 4 is root 2. And then we get a 1 over root 2 here. we can, why not? We can tidy that up a little bit. Factorize out the pi over 4 part, and I'm going to get 1 minus root 2 minus 1 over root 2. That is the minimum value on this interval. Okay, good effort, me included.